today we're going to learn about something called end behavior. A power function is a normal polynomial function, so that's going to be easily defined. So you have f of x equals ax to the nth power. Okay, so this is a power function. It says where a and n are non-zero real numbers. Okay, and for a power function, a is the leading coefficient, n is the degree. When you are finding the degree of a polynomial, you are looking for the highest exponent. Okay, so to find the degree of a function, you are looking for the highest exponent. Okay, and all they're telling you here is that these two values, a and n, are not zero. Okay, and a is the leading coefficient. So the leading coefficient is the number which we call it the LCO for short, leading coefficient. It's the value in front of the term with the highest exponent. Okay, so as our polynomials get larger, some of them might be given to you in standard form. Some of you might have to find what the degree is. Okay, and then a power function with a positive integer n is called a monomial function. So that's when you just have one term. So this is a monomial. A monomial is just a type of polynomial. Okay, so what we're going to focus on here is the end behavior. So the key concept here is end behavior. And as you're looking at these, what we're going to do is we're going to try to come up with some rules of similarity. Okay, so some of these graphs have things in common. I want you to look at the two even graphs and see if you can find something the two even graphs have in common. So two of the graphs say the degree is even. Okay, can you highlight which two are even? And then I just want you to talk to your row about what you notice about the two even ones. Okay, so the two even are here and here. Okay, so Gloria and Andy, what did you guys say about both even graphs? What did you guys notice? Okay, yep, in this case they are both parallel. Good. Okay, Addie, what did you and Caleb discover? That they were quadratic? Okay, good. Did anybody say anything else besides that? All right, then let's look at the two odds and let's see how they're different. So if you have an odd degree, yeah, what? Oh yeah, they're both here at the origin, yeah. Good. All right, and then I want you guys to do the same thing with the odd. So what do you notice about the odd? So I want you to look at their ends in particular. So what do you notice about the ends of each one? Yep, if they're odd. Okay, so each one is going to have two ends. What do we notice about the odd ones? Yeah. Okay, so if they're odd, they're going to go in different directions. With the evens, what do we notice about both of those ends? Yep, they're going in the same direction. Okay, so anytime your degree is an even degree, we know that the ends are going to be going to either positive infinity or negative infinity is what we say. Okay, so your degree, we're going to write it here. Okay, your degree can either be even or odd, and if it is even, the ends go in the same direction. And if it is odd, the ends go in opposite directions. And that's a really simple way to remember which is which. The odds go in opposite. You have that alliteration there. All right, now the other thing that they notate in these graphs is the leading coefficient. So the leading coefficient can either be positive or negative. That's what you're going to look at. So in the first two, the leading coefficient is positive. In the second two, the leading coefficient is negative. So again, I want you to come up with some type of rule. So every time you know the coefficient is negative, the leading coefficient, what happens? Every time it's positive, what happens? Okay, so take a second to think about that, and then I'll have you talk with the people in your row. Okay, so I want you to talk to the people in your row, come up with some pattern. So every time the leading coefficient is positive, what happens? All right, so let's look at the negative first. So look at these two graphs. What's the same in these two graphs? What's the same? Of what side? Yeah, on the right side, they're both going to negative infinity, right? Here and here, aren't these parts of the graph the same? Let's highlight them so we can see that. Okay, and then if we look at the positive, the parts that's the same, you have the right side again, that's the same. So if it's positive, we say that it rises on the right or goes up. Okay, and if it's a negative, then it's going to fall on the right or go down. Okay, but it's all about the right side. Okay, so what we're going to do is we're going to look at these end behavior statements. Okay, I want you to read through those real quick. And then we're going to label them to hopefully make more sense of what those symbols mean. And after you've read through them, I want you to see if you can notice something that's contained in every single one of those statements. This is I put the O instead of the C first, so this is the leading coefficient. This is the LCO. I know it looks bad. I'm sorry. Yeah, it's just the leading coefficient, the LCO. This looks like local to me. Okay, so what is the same in every single one of the M behaviors? What does every single one have? They all have infinity and negative infinity. Yep. Let's go more specific. So what always goes to negative infinity? What always goes to infinity? Don't they all start the exact same? As x goes to negative infinity? As x goes to negative infinity? Yeah, so the reason why they all start like that is because when x goes to negative infinity, what that means is that's the left side of the graph. And every single graph is going to have a left side and a right side. So what this means is, as x goes to the left, f of x goes, and then this either means up or down. So if it's f of x, this is going to be going up. If it's going to positive infinity, it means it's going up. And then as x goes to positive infinity, that's going to be on the right side. So every single one of these starts as x goes to negative infinity, and then the second one is always as x goes to positive infinity. Every single graph is going to have a left side and a right side, but not every single graph goes up or down. So the f of x, that depends on what your graph looks like. For example, on the left side of this graph, it's going down. That's why it's going to negative infinity. On this side of the graph, it's going up. That's why it's a positive infinity. Okay, and some books actually do put a plus in there. This book doesn't, so we're not going to write that in. And then if both of the ends are going down, then you would use a negative infinity is where the f of x is going. Okay, f of x is your output. On this one side is going up, the other side is going down. So what we're doing is we're using those symbols to help communicate what each side of the graph is doing. So when you guys are writing your end behavior statement, okay, we're going to write this here. The end behavior statement is going to be the same every time. So when you are writing this yourself, you can always start off with as x goes to negative infinity, f of x goes to, and then we're going to fill that part in. And then on the other side, it says f of x goes to positive infinity. Okay, and we do need to practice to make sure that our infinities look decent. I don't expect perfection, but I should be able to tell what it is, and it should not be an 8. Okay. And if you're really, really struggling, you can always put like 2 ovals next to each other. That's fine. Or you can just do a sideways 8. Okay. All right, so you are going to be filling those in. Okay. So the rule is, if you are talking about the x value, okay, then x is either left or right. Left is negative infinity. Right is just infinity. So these mean 2 different things depending on what you're talking about. So if you're talking about f of x, then negative infinity means down, or positive infinity means up. Okay, so on the left side of the graph, where does the end go? Up or down? On the right side of the graph, where does the end go? Up or down? Okay, and then you're also going to have to say what the domain and the range are. Okay, and if you look here, see they gave you what the functions were. This was x to the 4th, x to the 5th. negative x squared, negative x cubed. Okay, so your domain for all of these is all real numbers. We're going to be writing the domain and range in interval notation. So for all real numbers, you can always write negative infinity to infinity. You don't have to write that out every time. You know that it's negative infinity to infinity. And then for your range, you have some different options. So the first one is all real numbers that are greater than or equal to 0, because they're all at 0 or above. So at 0, you would need a hard bracket because it includes it. And if they're all above, it goes to infinity. Okay, you guys might remember that from our early days in chapter 1 when we were doing a bunch of domain and range. Okay, and then 2 of them have a range of all real numbers as well. So it's all real numbers if you have, what is your degree? Odd. Yeah. And that's because you're going from negative infinity to infinity. Okay, you're going from negative infinity all the way to infinity, so both of those are your all real numbers. Okay, so negative infinity to infinity for both of those. And then the last one, your range is all real numbers that are less than or equal to 0. So if it's a less than or equal to, that means you start at negative infinity and you go up to 0. So if they're all below that value, you start with the lowest value at negative infinity. All right, and then for example 1, we are going to describe the end behavior of each function using the leading coefficient and degree. Okay, and then we're going to state the domain and range. Okay, so if they ask you to use the leading coefficient and degree, then we need to show that that's what we're using. Okay, and then anytime you are stating the domain and range in this section, you're going to do interval notation. All right, so we're going to do our degree and our leading coefficient. Okay, so the degree is the highest exponent, which means your degree is 6. The leading coefficient is that value in front, so that is 5. So your degree is always about, is it even or is it odd? So 6 is an even number, and if it's even, they're going in the same direction. The leading coefficient is either positive or negative. So if it's positive, it's going up on the right side. Okay, so what we're going to do when we create our function is we're going to use this end behavior statement. So it says x goes to negative infinity, f of x goes to, and we'll fill that out in a moment. Okay, so we're going to fill this out according to the degree and the leading coefficient. Now, if they tell you that it's positive, if you found that it was positive and it goes up on the right, this is the right side, the positive infinity. So if that's the right side, I know that it's going up there. So I'm going to fill that one in first. Okay, so because that's the right side, I'm filling that in first. Then, if it's even, I know they're the same. So if that's positive infinity, this is positive infinity. And this is going to be your statement. Okay, this is your end behavior. Okay, now for the domain, we know the domain is all real numbers for every single one. So if we write that in interval notation, it's negative infinity to infinity. Okay, now if it's going up on both sides, that's going to be just like this first graph that we have here. It's going up on both sides, then our range is going to start at 0 and go to positive infinity. Okay, so based on that, I want you guys to do part B. So remember that your first step is always saying your degree and your leading coefficient, okay? So if your degree is 5, we know that's odd and that these should go in opposite directions. And then if your leading coefficient is a negative, then it means it's going to go down on the right side. So it's always about the right side. You're always going to fill that in first. So you can start with the left, and then you have the right. Okay, so if it's going down on the right, this would be negative infinity. If they're opposite, this has to go to positive infinity. Now remember, anytime it's odd, your degree is odd, what does that tell you about your range? All real numbers. So anytime it's odd, your domain and range are going to be the same. All real numbers. Okay? All right, so now we're going to use our graphing calculator in example 2. A scientist models changes in ocean density layers by using this given function where x represents the distance from the equator. We're going to graph the function. We're really just going to do a rough sketch of it from our graphing calculator. Okay, and then we're going to state the domain and range. And then it says round to the nearest 100 if necessary. It is 100 because you're not 100 because your value is going to be in the hundreds. Okay, so for any of the story problems, when they ask you to graph, you can just draw a rough sketch. From your graphing calc. Okay, but we want to be able to see the entire shape of it. Okay, so we're going to draw a rough sketch from our graphing calculator. We're going to plug that in. So you are going to have to adjust the window to see the full graph. And then, Jake, when you adjusted your window, what did you use? Was there anything in particular? Do you play with the window, or do you use like zoom fig or zoom out? You play the window, okay. So when you're adjusting the window, okay, so we're plugging this in for y, so 0.006 x to the fourth minus 0.7x squared minus 100. When you graph in that window, nothing shows up. Okay, so if you graph in your standard window, you can't see it. Okay, so one thing you can do is you can play with the window yourself. What point do you know is on your graph? Because of the equation. Yeah, negative 100, right? So we're at least going to have to go down to negative 100. Okay, and then you can't see anything here, so you could adjust that. Sometimes you can do the zoom in. Oh, sorry, the zoom out. That's what I meant, because you can't see that. Okay, so sometimes you can do the zoom out. I'm going to press it again in a second. And then, I don't know if you guys can see this thing working in the corner there, but that's taking way too long. So I'm turning it off and on. Follow me for more problem solving tips. Okay, so you have this, you have your graph. Okay, so I'm going to go to zoom, I'm going to go to zoom out. Yay, I have a line. I have another line. Okay, so I'm going to go to my, well, actually, I'd probably zoom out again. I'd probably zoom out one more time and see what happens. Okay, so now I can see this a little bit better, but I want to see what's happening below, so I'm going to go to my window. So I'm at negative 160. Maybe I would try negative 300 and see what I get. That's actually pretty good, but I want to be able to see like the whole bottom, so maybe I would go to negative 400. Yay! Okay, so now I can see that whole graph there. So we're just going to draw a rough sketch of what we see. This is a very common quartic function, x to the fourth. Okay, so when you are trying to find the domain and range, we know what the domain is going to be, right? What has been our domain all day? What's our domain? Yeah, negative infinity to positive infinity. When we're trying to find our range, keep in mind that your range should always go from the lowest y value to the highest y value. Now, one of those is going to be infinity or negative infinity. So based on this, do we know the lowest or the highest? We know what the highest value is because it's going to infinity. So we can put in the infinity there. Now the lowest value is going to be this minimum. So what we're going to have to do for this one is we're going to have to use the minimum feature. Okay, you do not just want to trace it because that's not going to give you the value. And when you use the minimum feature, you're going to have to find the y-coordinate because remember the range has to do with the y's. So just like we've done before, we're going to do the right bound, we're going to do the left bound. And my guess. Okay, so for the minimum y value, I got negative 304.17. We're rounding to the nearest 100. So that means it's either going to round to negative 300 or negative 200. This one's going to be closer to negative 300. So everything is above your negative 300. Okay, and then if you did the minimum value on the other side, you can see these are symmetric. Okay, it doesn't matter which one you find the minimum for. Okay, it's going to round to that negative 300. All right, and then I'm going to give you a minute to read through this polynomial paragraph, and then we're going to talk about some of our key points, okay? Take a few more seconds to read that, and we're going to pull out some key points. All right, so it says a polynomial in one variable is an expression of this form, and then there's this big, long, complicated polynomial. All this is telling you is that if you have a polynomial that starts with something like x to the fifth, right? It could be like 6x to the fifth. The next thing you would have, if your n value is 5, see how this says n minus 1? So they're just saying that the next thing would be 4, and then x to the fourth. Okay, minus 2, x to the third. Plus, and then it's like the dot, 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 because you could have however many. If this was a 6, you'd have another one in there, all the way to x squared, x to the first, and then there'd be no x value. So that's just a way that you write any polynomial. Okay, and then it tells you that a cannot be 0. A sub n minus 1, a sub 1, and a sub 0 are real numbers. Those are just coefficients. And then n is a non-negative integer. So we're going to talk about that part. N is a non-negative integer. Okay, so n is the degree of your polynomial. Okay, this is called a polynomial in one variable because the only variable you're going to have is your x term. So if n is a non-negative, that means that your exponent cannot be negative. So there are no negative exponents. And you would have briefly talked about negative exponents in Algebra 1. Okay, if you have a negative exponent, it could look like this. If you have x to the negative n power, that's the same thing as 1 over x to the nth. You would have talked about that when you did exponential relationships. which we'll go over again this year. Okay, so that's what it means by non-negative exponents. You can't have your exponent be a negative, but you also can't have the variable to a power underneath a value. So it can't be in the denominator there. Okay? And then if it's an integer, that means you have no fractional exponents. Or square roots. So you can't have any fractional exponents or square roots. So you can't have like x to the 1/2 power. Sorry, that went into my square root. You can't have x to the 1/2. And most of you probably don't know this, but x to the 1/2 does mean the square root. And that's something we'll talk about later in the semester. Okay, and then this says because the terms are written in order from greatest to least degree, this polynomial is written in standard form. So most of the time you are going to have your polynomials in standard form. That's actually what you're used to seeing, but they do not have to be given to you in standard form. So when they are in standard form, the exponents go in order from greatest to least. So you start with the highest exponent. So in standard form, exponents go in order from greatest to least. Okay, so you start with the largest value and then you go in order decreasing. Okay, so it's in standard form if they are going from the greatest to the least degree. Okay, and then this is the degree of the polynomial is n. Okay, and the leading coefficient is a sub n. A sub n is just the notation they give for the leading coefficient. Okay, it's just a number. Okay, and we are going to have to find the degree. So remember, the degree is always what? Do you guys remember from the first page? It's going to be your highest exponent. So you're going to have to find the degree. You're going to have to find what the highest exponent is. Okay, so the polynomial functions that we're going to be working with are continuous functions, and they can be represented by a polynomial equation with one variable in that. So it says you've learned about constant, linear, quadratic, and cubic. We haven't done anything with cubic. That's a little bit later in this book, but it's to the power of 3. And then other functions are quartic functions, which is a power of 4, and then quintic functions, which is a power of 5. Did you guys know that? Did you guys know the quartic? Okay. I can't remember if you talk about those in geometry or not. Okay, so the degree is going to tell you the maximum number of times that the graph crosses the x-axis. So whenever they ask you to find real zeros, you're going to use the degree. So the degree equals the max number of times the graph crosses the x-axis. And notice it says it's the max number of times. So if it's the max number of times the graph can cross, you can have it cross less than that. So it's just the maximum number of times that it intersects the x-axis. Okay, the max number of times that it crosses your x-axis. Okay, so example 3, it says to state the degree and the leading coefficient of each polynomial in one variable. Okay, if it is not a polynomial in one variable, you have to explain why. So if you have to explain, you need to write a sentence. It's going to be a very short sentence about why it is not a polynomial in one variable. Okay, so for A, your polynomial is 8y plus 7y squared minus 9y cubed minus 15y to the 4th. I just want you to write down the degree and the leading coefficient. Okay, so what's our degree for A? 4. That's the highest exponent. Okay, what's the leading coefficient? Not 8. Negative 15. Yep. Okay, so this one, is this in standard form? No. Okay, so when it's not in standard form, remember that your leading coefficient, okay, is always going to be in front of the variable that has the highest exponent. Okay, it doesn't say that you have to write this in standard form, okay, but you could. You don't have to. You don't have to do that on your homework. But if you did write it in standard form, it should be the first value. Okay, so if this was in standard form, that would be the first one there. Okay? All right. Now, sometimes they're going to have like an f of x equals, sometimes they won't. This is f of x equals negative 6, x to the 6th, minus 4x to the 5th, plus 13 over x squared. And c is ab squared plus a squared b to the 4th. Okay, so I'm going to tell you that both of these are not polynomials, and I want you to see if you can come up with a reason why. Okay, so both of those are not polynomials in one variable, and I want you to come up with a reason why. And if you're not sure for B and you just didn't want to go to C, that's fine. Okay, it looks like we're getting stuck on B, so let's remind ourselves what we need for there to be a polynomial in one variable. Okay, so we can't have negative exponents and we can't have fractional exponents. One of these is hiding in part B. So if you look here, you have the x squared in the denominator. What this really means is this is 13x to the negative 2. Okay, so that is a negative exponent. Okay, so when you're writing out your explanation, you can say it's not a polynomial because we can't have a negative exponent. Okay, so it's not a polynomial because you can't have a negative exponent. Okay, and you have the 13x to the negative 2. Okay, I would also let you say, you could say or because you can't have a variable in the denominator. And that would be fine too, but you have to make sure you specify it's a variable. Okay, so you can't have that variable of x in your denominator. All right, and then these are called polynomials in one variable. So what's the problem with C? There's two variables. So you're just going to say not a polynomial because there are two variables. Okay, and that's it. So a very short sentence. Okay, so not a polynomial because there are two variables. So guys, if you're just coming in, I don't want you hurrying to get all this down. I want you to listen to it and take your time. Okay, so just jump in with us right here at example 5. Okay, so we're using the graph to state the number of real zeros of the function. Notice there's that keyword real. That's not going to include imaginary zeros, which we've talked about in here before. So when you're trying to find the real zeros, all you're trying to find are the x-intercepts. So I want you to write just a little note that the x-intercepts are equal to the real zeros. Okay, the x-intercepts are equal to your real zeros. So all you have to do is count the x-intercepts. So let's look at A. How many x-intercepts are there on graph A? 3. So then your answer is just 3. Okay, they're just asking you to state the number of them. You don't even have to find what they are on X, so there's 3. Okay, and then for B, how many are there? 2. 1, 2. Okay, so that's all you have to do for that one. You have to know the real zeros are your x-intercepts. Okay, now this last one is putting everything we've done together. So you're describing the end behavior, you're stating the degree and the leading coefficient, and then if the function is not a polynomial, you're going to explain why. Okay, so for A, we have g of x is equal to 2x to the 5th plus 6x to the 4th. Okay, and I want you to write what your degree and leading coefficient is, if you can. And then you can do your end behavior from there. Okay, so when you're finding the degree, who can remind us how we find it? Yeah, so you're going to find the greatest exponent. Okay, so the greatest exponent is what? What'd you guys get? 5. Yep, great. Okay, and then what's your leading coefficient? 2. And it's always what's in front of your greatest exponent. So this is in standard form, so that's great. Okay, now when you're writing your end behavior, remember how we talked about you can always start it like this, as x goes to negative infinity, and then this is called g of x, so we'll say g of x goes to, and this is as x goes to positive infinity, g of x goes to. Okay, so then all we have to do is assess what we've already found. The degree is odd, the leading coefficient is positive. So if the leading coefficient is positive, that means that you're going to go up on the right side. So this should be positive infinity. And then the degree here is odd. Okay, if it's odd, what does that tell us about these two values? They're going to be opposite. So if I go to positive infinity on the right, I'm going to go to negative infinity on the left. Okay, now B looks a little bit different when you first start it. So it's h of x equals x plus 5 multiplied by 3x minus 4. Okay, to see if it's a polynomial or not, we're going to have to expand this using what? FOIL. Okay, so I want you guys to FOIL, and then you can go ahead and do your other steps, okay? So once you FOIL this out, you guys are doing the degree, the leading coefficient, and your end behavior. All right, so then for this one, what was our degree? 2 is our highest exponent, which means our leading coefficient is 3. And then with the degree, you're asking is it even or odd? With the leading coefficient, you're asking is it positive or negative? Okay, and then your end behavior is always going to start as x goes to negative infinity. And then you're going to fill in where the end goes. And as x goes to positive infinity, where does it go? So if it's positive, on the right side it goes up, so this should be positive infinity here. If it's even, they're both going in the same direction, so it should be positive infinity here.